Pluto, a remote and mysterious heavenly element, was previously perceived as a particular and substantial planet inside our planetary group. It was viewed as a component of the planetary family until later interesting attestations by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into focus. These distinguished specialists have made a stunning statement: Pluto could be on a potential collision course with Neptune. Yet, how could such an event even happen? What might be the consequences of such a colossal occurrence? Are we witnessing an exceptional cosmic peculiarity, or is there more to this approaching heavenly event than what initially seems? Join us as we explore the potential outcomes of a hypothetical Pluto-Neptune collision. Pluto, once classified as a planet but later redefined as a dwarf planet, continues to intrigue and captivate the interest of astronomers and researchers within the vast universe. Studies by top space scientists suggest Pluto's orbit lies perilously close to Neptune's. Eminent astrophysicists like Tyson and Kaku have voiced concerns over the potential dangers of a collision between these two celestial bodies, which could present a significant risk to Earth. But how could such a devastating event unfold? Pluto's orbit around the Sun is distinct from any other planet in the solar system. It takes an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto has not yet completed even one full revolution around the Sun. However, the intrigue doesn't end there. Pluto's orbit is characterized by an unusual shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's path even more peculiar is its 17-degree inclination relative to the ecliptic plane, making its orbit far more eccentric compared to other planets. This inconsistency introduces additional complexity to Pluto's orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune. For about 20 years in each orbit, Pluto actually crosses inside Neptune's path around the Sun. This defies expectations based on their respective positions within the solar system. This raises a clear question: why hasn't Pluto collided with Neptune yet? The answer lies in the gravitational interactions of other planets within the system. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers were puzzled by its irregular trajectory. Unlike other planets, whose orbits align closely with the ecliptic plane, Pluto's orbital path stood out due to its steep inclination and eccentric shape. The mystery surrounding Pluto's orbital behavior can be explained by a concept called the three-body problem in celestial mechanics. This theory aims to understand the movements and interactions of three objects: Pluto, Neptune, and the Sun, under their mutual gravitational forces. For Pluto, this problem demonstrates that the orbits of Pluto, Neptune, and the Sun interact in a complex manner. Key terms like apsidal libration, node libration, and Vesk wobbling are critical to solving this puzzle. Astrophysicists hypothesize that the reason all planets maintain their orbits is due to a phenomenon called libration. In the case of Pluto and Neptune, when Pluto crosses Neptune's orbit, their relative positions are offset by about 90 degrees. This separation is crucial in preventing their orbits from overlapping and resulting in a collision. Additionally, libration refers to the vertical oscillation of a celestial body within its orbit. For Pluto, this means that when it comes closest to Neptune or another massive planet, it is positioned significantly above the plane of the orbits, further safeguarding it from potential collisions. Another critical factor in this equation is the Vesk wobbling, named after the researchers who first studied how objects move in space. The Vesk wobbling refers to how the gravitational forces exerted by Pluto, Neptune, and the Sun influence each other's motion. This intricate dance of gravitational interactions helps maintain Pluto's orbit, even when it follows an unpredictable trajectory near the Sun. The Vesk wobbling is essential in ensuring Pluto's orbit remains stable for incredibly long periods despite the apparent randomness of the system. This phenomenon ensures that despite the seemingly chaotic nature of Pluto's orbit, certain forces and patterns help keep everything in balance. These gravitational forces and phenomena play a vital role in maintaining Pluto's orbit, thus preventing potential collisions with Neptune or any other celestial object. The three-body problem is integral to understanding how objects in space interact with each other. It reveals insights into Pluto's motion and helps astronomers comprehend the gravitational effects on other distant celestial bodies, including stars and planets. Numerical simulations from the late 1980s demonstrated that despite Pluto's peculiar orbital dynamics, its trajectory remains stable with only slight variations from its original conditions. These characteristics of Pluto's orbit have remained consistent over extended periods, allowing astronomers to refine their understanding. Later, virtual simulations also provided clarity on how larger planets like Neptune, Jupiter, and Saturn influence Pluto's orbit. Neptune shares a unique relationship with Pluto through a 2:3 orbital resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit. However, Neptune's gravitational force is not the only influence. Jupiter's immense gravitational pull also plays a significant role in ensuring Pluto's orbit remains stable. Saturn's gravity further contributes to the stability of the outer reaches of the solar system. Studies suggest that Jupiter's massive gravity is sufficient to keep Pluto's trajectory consistent for extraordinarily long periods, potentially billions of years. Together, Neptune, Jupiter, and Saturn may be working in harmony to keep Pluto's path on track, preventing disruptions to its orbit. These anomalies in the planetary system are crucial in maintaining stability within the solar system. Without these forces, the universe could be far more chaotic, with objects like Pluto possibly colliding with other bodies or being ejected from their orbits, resulting in conflicts among celestial objects. The complex relationship between Pluto's orbital pattern and Neptune's highlights how neighboring planetary systems function and interact. Pluto's case illustrates that even in seemingly chaotic orbits, harmony can be achieved through the intricate interplay of gravitational forces and orbital mechanics. This dynamic emphasizes the importance of ongoing observation and investigation to maintain our understanding of the universe. Studying space often compels us to confront the unusual and unpredictable nature of celestial bodies. Pluto's orbit serves as a prime example of this unpredictability, showcasing the potential for orbital resonance and the fundamental connection between Pluto's and Neptune's trajectories. The 2:3 orbital resonance ratio between Pluto and Neptune ensures that despite their crossing paths, they never collide. This resonance is a crucial principle in celestial mechanics, preventing any catastrophic interactions. For each 2 orbits that Pluto completes, Neptune completes 3. This delicate balance stabilizes their orbits, demonstrating how even seemingly chaotic systems in space can self-regulate through subtle gravitational forces. In addition to Neptune's influence, other massive planets like Jupiter, Saturn, and even Uranus play significant roles in maintaining stability within the solar system. Jupiter's immense gravitational pull acts as a safeguard for smaller bodies like Pluto by influencing their orbits and preventing them from straying off course. Some researchers even suggest that Jupiter's gravitational force may have been instrumental in preventing Pluto from being ejected from the solar system altogether. Together, these forces underline the importance of understanding the gravitational interactions at play within our planetary system. While Pluto's orbit remains stable for now, changes could still occur in the distant future. Astrophysicists like Neil deGrasse Tyson continue to explore the complexities of the universe, providing deeper insights into the delicate balance governing the movements of celestial bodies. The possibility of a Pluto-Neptune collision, although unlikely, serves as a reminder of the ever-evolving and intricate nature of the cosmos. It highlights the necessity for continued exploration and study of the forces that shape our solar system. The ongoing study of Pluto's orbit and its interactions with other celestial bodies is not only essential for understanding our planetary system, but also for unlocking the mysteries of the wider universe. As scientists like Tyson and Kaku further examine space dynamics, they emphasize the evolving nature of celestial mechanics and the challenges of predicting the future movements of planets and other heavenly objects. The potential for a Pluto-Neptune collision, though improbable, reminds us that the universe is full of uncertainties. Even the most stable systems can undergo immense changes over time. Moreover, the intricate gravitational interactions among celestial bodies reveal the beauty and complexity of the cosmos. They underscore the importance of maintaining vigilance in our studies, as the dynamics of space have profound implications for our understanding of planetary stability and the potential risks to Earth and its neighboring planets. Through further research and exploration, humanity can continue to unravel the mysteries of the universe, ensuring that we remain prepared for any eventualities that might arise in the cosmic dance of celestial bodies. Where the developments of celestial bodies are intricately interconnected, the 2:3 orbital resonance between Pluto and Neptune ensures that despite their intersecting paths, a collision is avoided. This resonance is a direct consequence of gravitational interactions between the two bodies, establishing a delicate balance that has preserved Pluto's orbit for billions of years. It serves as a perfect example of how gravitational forces in seemingly chaotic systems can produce stable and predictable outcomes over long periods. The significance of this resonance cannot be overstated. It is a fundamental principle in celestial mechanics, demonstrating how even irregular and complex orbital patterns can maintain harmony through subtle gravitational influences. This understanding of resonance also extends to the broader dynamics of the solar system, where the interactions between planets, dwarf planets, and other objects are critical in maintaining stability within the system. Jupiter, in particular, plays a significant role in the overall stability of the solar system. Its massive gravitational influence acts as a protector for smaller bodies like Pluto, preventing them from being ejected or colliding with other objects. Jupiter's gravitational field extends far beyond Pluto, affecting the orbits of asteroids, comets, and other small bodies in the outer solar system. This further illustrates the interconnectedness of various objects in the solar system and how their gravitational forces work together to preserve equilibrium and order. Some experts even suggest that Jupiter's gravitational forces may have played a role in securing Pluto's place in its orbit, preventing it from being ejected from the solar system. This scenario highlights the importance of understanding not just individual objects, but also the broader forces at play within our solar system. The study of Pluto's orbit and its interactions with other planets also emphasizes the fluid nature of space. While mathematical models and simulations offer valuable insights into the behavior of celestial bodies, they also reveal the inherent uncertainties in predicting long-term developments. Minor changes in initial conditions or slight deviations in gravitational forces can lead to vastly different outcomes over time. This uncertainty serves as a reminder of the complexity and unpredictability of space, highlighting the need for continuous observation and analysis to refine our understanding of the forces that govern the universe. In the larger context of space exploration, Pluto's orbit offers fundamental lessons about the balance of forces that determine the behavior of celestial bodies. The fact that Pluto's orbit has remained stable for billions of years, despite its eccentricities, speaks volumes about the power of gravitational force and the self-regulating nature of orbital mechanics. This case underscores the critical importance of ongoing research and the need to continually improve our models of how planets and other celestial objects move through space. The continued study of Pluto's orbit and its relationship with other celestial objects provides valuable lessons about the intricate balance of forces that govern how bodies move in space. As the study of space continues to advance, it is clear that understanding the delicate interplay of gravitational forces and orbital mechanics is essential not just for understanding Pluto's trajectory, but also for uncovering the broader dynamics that govern the solar system and the entire universe. By studying systems like Pluto's, scientists gain a deeper understanding of the forces at work in the universe, allowing them to better predict the behavior of other objects in space. Despite Pluto's orbit being stable for billions of years, the complexity of its movement and interactions with other celestial bodies continues to intrigue the scientific community. This unpredictability in the movement of celestial bodies is a key reminder of how dynamic space truly is. The possibility that Pluto's trajectory could change in the distant future, whether due to external forces or shifts in the gravitational influences of nearby objects, serves as an important case study for understanding cosmic stability and instability. Even with the current stable trajectory, Pluto's orbit continues to remind us that our understanding of space must always remain adaptable to new discoveries and changing data. The fact that Pluto has remained in orbit around the Sun without significant modifications or disruptions, despite the seemingly chaotic nature of its path, underscores the resilience and stability of celestial mechanics. Even when its path intersects with Neptune's, the gravitational resonance between the two bodies prevents any catastrophic scenarios from occurring. This stability is an ongoing testament to the power of gravitational interactions in keeping celestial bodies on course for such extended periods, despite the apparent unpredictability of their orbits. What is equally fascinating is the role other celestial bodies, especially Jupiter, play in maintaining Pluto's orbit. Jupiter's immense gravitational field exerts a far-reaching influence that stabilizes the orbits of smaller bodies.